you know, like, who's it?
It's Jeff.
That we can use?
Willie.
What?
You can break it up so Will.
Willie.
Will I am.
Let's move on. So just warning, we treat this symbol as a single unit, which has meaning the derivative. But of course, what it is it's really like delta y over delta x, and it's the limit as delta x approaches 0 of delta y over delta x. So one really nice thing about the Leibniz notation is that it reminds us of the humble origins of the derivative as a slope, right? Delta y and delta x are actual small quantities, and thus when you divide delta y by delta x, you get an actual fraction, and that's the slope of a secant line. But dy dx is like an infinite slope, so it's like a tiny slope. So the derivative is not a slope. The derivative is the limit, but it's the limit of a slope. Okay. The point of all of this is, even though the derivative is not a ratio, since it is the limit of a ratio, it retains many of its properties of a ratio. And one of the famous times in which a derivative acts like a fraction is in this thing called the chain rule. And here's what the chain rule says. The chain rule addresses how to differentiate a function inside of another function. And here's what it says. The chain rule says, and then we're going to talk about this for a while. The chain rule says if you take the derivative of f of g of x, then this is, well, I'm just giving you, it seems weird to just be giving the answer, but oh well, I guess this is what I'm going to do. This is the derivative of f evaluated at g times the derivative of g. Okay. And what is this actually saying? So now this is an informal way of thinking about this. Well, actually it's not, well yeah, I guess it's informal. The informal way of thinking about this is that what we're doing is we're taking again the derivative of the f of g of x function. This is kind of like the derivative of f of g of x with respect to x. This is kind of what this is sort of the way of thinking about this is that this is, well, it's like the rate at which f of g of x is changing with respect to g of x times the rate at which g of x is changing with respect to x. That is what the chain rule tells us. The chain rule says if you want to differentiate f of g of x, the answer is it's the rate at which f is changing with respect to g times the rate at which g is changing. And if you think of a derivative as just a fraction, then this actually makes total sense, because what you're doing is you're taking the f prime of g of x is the rate of change of f of g of x with respect to g of x, and the derivative of g is the rate of change of g with respect to x. And what's happening is these two just kind of cancel. Right? All right. Before we go any further with this, maybe what we should do is take some kind of close look at what's really going on in the chain rule. And for this, I think we need a giant picture. So let's make this a giant picture. I'm going to go here. In order to understand the chain rule, I think, and understanding the chain rule, so we have two objectives today. One is learning about the chain rule, understanding the chain rule, proving the chain rule, and getting good at using the chain rule. And all of those are worth doing. But right now we're on the understanding part. So let's talk about composite functions, because to really understand the chain rule, you have to have a pretty sophisticated understanding of composite functions. functions nested inside of other functions. Okay, f of g of x. What? So this is just like algebra 1. What's the first thing? Let's tell the story of what a hero x goes through in order to produce the f of g of x output. Where does he go first? Into g, and then the output goes into f. Right, so in fact, what we could imagine is that x lives somewhere over here in the domain of g. So this is the domain of g, and so x lives here. And what happens when x goes into g is he gets transformed in some kind of way, right? And so we can draw, I hope you drew these kinds of pictures with Giles last year, at least a couple times. Over here, what we have is the range of g. So this is the set of all possible inputs to g. This is the set of all possible outputs. And when we plug x into g, what happens is, it lands over here in g of x. So we get a little action like this. This is what the g function does in this sort of abstract sense. It matches an input to some kind of output. All right, and then what do we do with that output? Put it in f. We put it in f. And so it better be true in order for this function to be defined for input x. It better be true that this particular output, at least, is also in the domain of f. Okay, so I'm going to draw this schematically like so. This new circle here, this is the domain. This is the domain of f. And it's the intersection of the range of g and the domain of f, which provides the possible landing sites for g of x, right? Because if g of x lands here, then I can't plug it into the domain of f, follow? Okay. And if something were here, then there would be no way to get there. All right, but so there's this, hopefully there's this healthy overlap, and then what next happens is that we have the range of f, and well, that's just what the f function does. The f function takes us from a particular element in its input to its output. And so here we get f of g of x. Okay, that is the static picture of what's going on. But calculus is the study of infinitesimal change, among other things. And so now what we have to do is we need to blur everything a little bit, right? We need to start our stopwatch and we can hit start and then stop immediately on the stopwatch. Have we talked about that before? That's kind of what the derivative is. The derivative answers the question, if, this is actually deep, the derivative answers the question, if you change x by a tiny, tiny bit, by how much does f of g of x change? I'm going to say that again because I think it's important, right? When we are asking the question, what is the derivative of f of g of x? The question we are answering is, how does this function respond to a small change in x? If I change x slightly, what effect does that have on f of g of x? Cool. So what happens? Let's change x slightly, and let's try to track those changes throughout the process. Okay. Instead of plugging x into g, I'm going to wiggle x slightly so that it becomes not x but x plus h. All right. What can I do with? What effect is that going to have? Someone talk to me. It's gonna. This is gonna change a little bit, right? It's gonna go, instead of landing at g of x, it's gonna land nearby at g of x plus h. Agree? Okay. What determines by how much the g function changes from this spot to this spot? Okay, clearly it depends on g, but specifically what property of g affects by the derivative? Yes, yes, right? That's crucial. I want everyone to realize that. It is specifically the derivative of g, which tells you by how much g changes when x changes a little bit. That's what the derivative is, right? Okay, so far, if I'm keeping a list of the things that matter to me, g prime matters, right? Because g prime is what tells me by how much I move from here to here. Okay, cool so far? Okay, and now what happens is I'm going to plug into the f function this number g of x plus h. And what's going to happen is a further movement. And this further movement is to, f of g of x plus h. Okay, what determines by how much f moves from here to here? Or what determines by how much f of g of x moves from here to here?
The derivatives of both of them.
The derivatives of both of them, but specifically, like now, it's the derivative of f which is relevant, right? Because I'm now plugging this number into f. The derivative of f to me is important because the derivative of f tells me by how much an input changes, or by how much the output changes when I change the input a little bit. Okay, but here's the subtle part. The subtle part is, so far we agree that the derivative of g is relevant. The derivative of f is relevant, but not the derivative of f at x. It's the derivative of f at g of x that matters. Because here I want to know, for a given input x, it is how fast g is changing at that point x, which determines by how much this moves. But now I'm plugging in the number g of x into f. Since I'm plugging in the number g of x into f, what's important to me is f's derivative, but specifically I want to know how fast f is changing when its input is g of x. Is this getting through? Hopefully. Right? It's the current value of g of x. It's how f moves when the input is near g of x that determines what this new shift is going to be. All right, so I hope, I don't know if this worked or not. I feel like it kind of half worked for some of you. What seems to be important is that g prime is important, g prime of x, because that tells me how much this first wiggle is going to happen. And the other thing that seems important is f prime of g of x. In other words, how much does the f function wiggle when you're inputting a number g of x into that function? All right, the chain rule is the thing that tells me that not only do these matter, but the way that they matter is that they multiply. The change in, I'm just going to rewrite this one more time. The change in f of g of x with respect to x is just, according to this new way of thinking about it, it's how much g changes for a small change in x times how much f of g of x changes with respect to a small change in g of x. And, did I mess up?
There's something in notation. You have like delta f of g of x and delta f of g of x. How do you differentiate?
So one more time?
So like you have on the left delta f of g of x and delta f of g of x. Oh wait.
It doesn't actually, never mind, right? Yeah, what this says, what this equation says is, hopefully if you're interpreting it the way I am, is that how much the f of g of x function changes when x changes by a little bit is equal to how much g changes when x changes a little bit times how much the f of g of x function changes when g of x changes a little bit. So this was supposed to be, it was this first thing that we all agreed was important, is this expression. And this second thing that we all agreed was important and relevant is this expression. And the chain rule says that these two are important, and specifically that how much the overall function changes when you change x by a little bit is just the product of these two. And that's not totally surprising that it's the product of these two, because it looks as if like we can just cancel the fractions. And that's because even though the derivative is not a fraction, it behaves like a fraction because it is the limit of a fraction. But before we even go any further in this, I want to so is this coming through? I feel like it's coming. I feel like it's going okay. Before we go any further in this, I want to stress how important this Leibniz notation is, how useful it is for us. For example, maybe I'll just go right to the example. So what's the formula for the volume of a cylinder?
R squared.
Oh, yeah. I know.
Pi R
Plenty of answers, many of which are wrong, but there's now consensus building, and the answer is
Pi R squared.
pi r squared h. Okay, right, because it's just, right, it's the area of the bottom and then just how many of those you have, right? Okay. We normally write things like this, right? That's how you did it in middle school or whatever. Okay, but if we want to get really technical about this, what kind of a function is this? No, I think I need more than one shh this time.
Because there's two things that are changing that you can't change.
No, only one.
You can change the height and you can change the radius.
Okay, you guys aren't saying what I wanted you to say, so I'll just say it. Yeah, it's like this is like a function with two variables. Okay, that sounds kind of hard, right? This is, suddenly we're doing like multivariable calculus or something. Technically speaking, this is just, in middle school you're just like, oh yeah, it's just like a formula, whatever, you just plug crap in. But really, if you want to get serious about this, this is a function which takes two inputs, and then the output of the volume formula depends on R and H. Okay, so this is just something to keep in mind. So if I suddenly just gave you this function and said, or gave you this expression and said, hey, what is the derivative of V? What's V prime?
With respect to what?
Yeah.
Exactly. Jimmy says, with respect to what? What are you changing? I know what the derivative means. The derivative is supposed to answer the question, how does the volume change with respect to a change in the input? But now there are two inputs. So suddenly, I can't do this anymore. Suddenly, what now I can do is something bold and awesome. Using the Leibniz notation, I can express the fact that I might change with respect to a certain variable. So I can ask questions like, what is dV dr? And if you fully understand the Leibniz notation, then this has a rich meaning. Would someone like to articulate what exactly is this saying? Richard Chen.
We're taking the derivative of v with respect to r, so that h is a constant.
Yeah. He says we're taking the derivative of v with respect to r. So in other words, when we're taking the derivative of v with respect to r, just like he said, we are temporarily treating h as a constant, and the variable which we're changing is the r variable, right? And so what is dVdr, just by using your formulas? If we temporarily treat h as a variable, then, well, like, what's the answer?
Pi H.
Yeah, so I put the pi and the h in the front, because they're just constants, and I just differentiate the r squared using the power rule, and then I just get 2r. Cool? Whoa!
Yeah.
2 pi r h.
That's the.
Does this sound familiar to anybody?
Yeah. Isn't that the small
You guys all like, passed the SATs and stuff, right? 2 pi r h. What is that?
Surface.
Yeah, that is the so-called
Lateral.
lateral area of a cylinder. Yeah, if you take a cylinder, well, if you take a cylinder and you everyone did the soup can and you unwrap it, then you get this rectangle, and the height of the rectangle is h, and the length of the rectangle is the circumference of the circle, which is 2 pi r, right? Pi d, that's the definition of pi. And so therefore it's the case that the lateral area of the cylinder is 2 pi r h. You cool? Okay. That's just like a coincidence.
Oh.
should like be blowing your mind. dv dr is 2 pi rh. In other words, the instantaneous rate of change of v with respect to r is 2 pi rh. In other words, if I change r by some infinitesimal amount, the amount which v changes by is 2 pi rh.
Because the sides are, because the top and bottom are constant.
Yeah, everyone's raising their hand. You're just saying whatever you want. But yes. Yeah, Didi Shetty, shoot your hand up first.
Because like if it's like if you imagine it as like a towel that you like wrap around the cylinder, you're like adding it every time you change the volume. When you make the radius bigger, you're like wrapping another towel around it, so the volume gets bigger.
Yeah, exactly. The Didi Shetty says, look here, take your cylinder and now wrap a towel around. This is like you dress like when you have a 5-year-old and it's like snowing outside, you put like 17 layers on him and he like doubles in volume. Right, so we wrap a towel, if we wrap a towel around the cylinder, that's kind of like changing the radius by a tiny, tiny bit. By how much new volume do I gain by changing the radius a tiny, tiny bit? The answer is like 1 towel's worth of volume, which is kind of just like the lateral area of the thing, right? And then you just wrap another towel around, okay, it's a little bit weird because it's infinite things. But yeah, the rate at which, if you think about the, if you just take a cylinder and you tell, it's like you're telling the cylinder, hey cylinder, grow by just getting bigger on all of your exposed surfaces, right? And then what it's doing is the rate at which the volume of the cylinder is growing is equal to the surface area of the cylinder, right? The more surface area you have, the more room for the thing to grow. It's like, and this is like how trees grow and stuff too, right? The rate of growth of a tree is, if you just keep adding a radius, the amount by which the volume increases is dependent on how big the tree is already. If this is all kind of making sense. All right, there's even one more way of looking at this a little bit cooler. If I now break all the rules of math, and this is what the Leibniz notation allows you to do, is to now do the opposite of what I said you were allowed to do, and we'll just treat this like a fraction temporarily for thinking purposes. So we'll write dv equals 2 pi rh dr. And what this kind of says is that the infinitesimal amount of extra volume added is the circumference times the infinitesimal amount of radius added. And if you think about it, if you add a tiny, tiny radius, then dr is like the infinitesimal thickness of your towel. And then the amount of volume added is actually just the volume of the towel, which would just be the thickness of the towel times the area times the lateral area of the towel. Follow? Okay, so this is actually, this line notation is actually awesome and allows us to express these kinds of subtleties. Okay, wait, before we call anyone else, let's do the other one. What is dv dh? Now we treat r like, no, careful Griffin, we treat r like a constant, and we differentiate with respect to h. So if h is the only variable, then it's just pi r squared, right? Yeah, so this is just pi r squared. Why does that make sense? Yeah, well, dv dh, in other words, how does the volume change with an infinitesimal change in the height? Just throw another CD on top of the CD spindle rack, basically, right? The rate at which this is growing is the area of the circle, because when you change the height by a little bit, you get another circle. Follow? Okay, so Leibniz notation is awesome. The chain rule is awesome. I feel like I'm doing this all in weird orders, but whatever. Let's prove it. Should we prove it? No. Seems like a thing to do. Let's prove the chain rule. The proof's actually like pretty easy for given how important of a theorem this is. The proof follows kind of straightforwardly from what we have been doing. All right. So let's go. Let's take the derivative of f of g of x. Step one is always the easy step. Use the definition of the derivative. Yeah, it's the only thing we can do. Yoni, what is it?
It's f of the limit is h approaches 0 of f of g of x plus h minus f of g of x all over h.
Yeah. Okay. What now? Can you think of anything to do now?
Could you like break up the limit?
Yeah.
And get like
Use the chain.
I'm gonna take a giant bite of peanut butter sandwich. Hint, it's like written all over both boards. I've done it already like twice.
Use the chain rule.
No, we're proving the chain rule. I hope you were kidding.
oh multiplied by the limit is h approaches 0 multiplied by the derivative of g of x over derivative of g of x.
Yeah, what is he talking about? Look, it's over here, right? This was informal. Informal.
John.
We said now that we've had this conversation, maybe this makes a little bit more sense now, right? Informally, the chain rule says that the rate of change of f of g of x with respect to x is the rate of change of f of g of x with respect to g of x times the rate of change of g of x with respect to x. And so what's missing from this thing is like this. I'm not doing a good job teaching. So what do we have to do? Yoni? Yeah, you gotta keep moving the camera.
Multiply that to the limit and multiply by the limit.
Actually,
No,
we can just
multiply
do
by-
algebra
yeah,
inside.
You just multiply by g of.
Someone else. You get it now. Someone else. What is he talking about? Do you guys see what's going on? I need to, oh, a tiny bit?
Wait,
Yeah.
multiplied by g of x plus h.
Oh, you guys missed it. No, that's not quite right. Right? This is how much f of g of x changes. This is how much the input x changes. So I need to multiply by the change in g over the change in g. What is the change in g?
G of x plus h or g of x plus h.
No, that's the value of g. I want the change in g.
Derivative g.
Wait, okay, watch. The really sloppy, crappy proof of this goes like this. Ready? Here comes the sloppy, crappy proof. Sloppy, crappy proof says, yo, how much does f of g of x change when you change x by a tiny bit? And here's what you do. You say, all right, man, I don't know. Let's multiply by change in g of x over change in g of x. And then you just, and then this becomes the change in f of g of x over the change in g times the change in g over the change in x.
Oh,
Like g of x.
This is g prime, and this is f prime at g.
Wait, this is g of x plus h.
So help, I kind of just told you what to do now.
so,
So what is it that I need to multiply by?
but
Yes. I multiply by change in g over change in g. And that's totally fine as long as, so this is okay as long as g of x plus h does not equal g of x. And there's actually a technical problem with this proof. So maybe a more advanced proof would deal with this technical problem, which can be dealt with in this really annoying way, which is in the appendix, but it's like not that interesting, so we're just gonna see. But yeah, I performed this algebra move, but it's like hopefully motivated this algebra move by like, you know, thinking. I don't know. I'm not sure if that works or not. Anyway, now what do we do? Switch and split up the limits, right? So we split this up into the limit as h goes to 0 of f of g of x plus h minus f of g of x over g of x plus h minus g of x times the limit as h goes to 0. Okay. So, what do we got now? Am I done? I'm kind of ish done. Yeah, but not really. This, I'm partially done. What's this? This is just G prime by definition. All right, here I need to do some stuff here. So, like a, yeah, exactly, right? Exactly, I'm going to do a limit switchy. So I'm going to say, all right, yo, let's let G of x be like A. This is how I thought to do it. And let's let G of x plus h, let's just call that some new variable like t or something. Okay, so, and now if I'm going to perform a limit switchy, I need to also determine what these things are going to as h goes to 0, right? So I guess it's just this one that's important. So as, so as h goes to 0, what can I say about g of x plus h? It goes to g of x. And what actual property of g am I citing by saying that as h goes to 0, g of x plus h goes to g of x? Almost. That g is continuous, right? This is actually basically the definition of continuity. That as h goes to 0, g of x, this says that the function, that g is continuous at x, right? So so since this is true, what that really means is that as h goes to 0, t goes to a, right? Okay, so given these two new variables and this new way of translating them, I can now rewrite these limits. Instead of writing this as the limit as h goes to 0, I'll write it as the limit as t goes to a of, yeah, Griffin's just doing math, right? F of t, because g of x plus h is t now, minus f of a over t minus a, times this thing, which is g prime of x. And what's that? By the definition of the derivative, this is specifically the derivative of f at a. Well, you good or you're zoning out? This is the derivative of f at a. So this is f prime of a times g prime of x. Are you impressed? And now a, of course, is some variable I just made up. A is g of x. So we have just proven that this is f prime of g of x times g prime of x. Cool? Cool. Okay, this is the chain rule. It is so amazing. It enables